Hi everybody, my name is Dr. Paul Kerstetter, and today I'd like to talk about implementing a mixer in an FPGA. A mixer can be used as a downconverter or an upconverter. Implementing a mixer in an FPGA is straightforward. It's essentially just a multiplier. For upconversion or downconversion, an additional filter is used. Mixers are a crucial component of software-defined radios, which I will briefly discuss in this video. Finally, I'll walk you through a short Vivado demonstration where I implement a mixer and used FIR filter GUI to achieve a downconverted signal. This is the presentation for how to implement mixers in FPGAs. A traditional mixer in IC design is the Gilbert cell mixer. Its purpose is to multiply an RF signal by a local oscillator in order to shift the signal's frequency. The mixer is composed of three main parts: a differential transconductance stage, which converts the RF input voltage into a current, and local oscillator-driven switch quad, which reverses the polarity of that current, and load elements that generate the intermediate frequency output. The LO operates at a fast switch rather than a linear amplifier. Because Gilbert cell mixers are fully differential, provide conversion gain, and offer good port isolation, they have become the classic active mixer used in RF integrated circuits. As shown in the slide, when a cosine signal at a frequency of F0 is multiplied by another cosine signal at a frequency of F1, trigonometric identities show that the output contains two frequency components, F0 plus F1 and F0 minus F1. In an FPGA, this same operation is performed digitally by using a multiplier where the cosine signals are sampled, quantized, and represented as binary vectors before being multiplied. In the slide, we see an example of a downconverter. The local oscillator is running at 100 MHz, while the input signal is at 90 MHz. At the output of the mixer, two frequency components are produced, 10 MHz and 190 MHz. These signals are then passed through a low-pass filter, which suppresses the 190 MHz component and allows the 10 MHz signal to pass. An upconverter, not shown in this slide, would instead use a high-pass or band-pass filter to suppress the 10 MHz component and allow the 190 MHz signal to pass. In this slide, we see a typical FPGA application where mixers are used, a software-defined radio, in this case, an FM radio receiver. From left to right, the FM signal first passes through a 20 MHz bandpass filter and is then 8x oversampled by an ADC with a sampling clock of 160 MHz. The ADC digitizes the analog waveform and sends it into the FPGA. Inside the FPGA, mixers are used to separate the signal into two quadrature channels known as I, in phase, and Q, quadrature, using LOs that are 90 degrees out of phase. Since FM channels occupy 200 kHz bands, a low-pass filter selects a single channel determined by the LO frequency F0. Because the 160 megasamples per second sampling rate is much higher than needed for audio, decimation filters reduce the sampler rate. Finally, the signal passes through an FM discriminator or demodulator to recover the audio. When using mixers, one issue is that they don't always maintain the desired word length. In the slide, it shows that multiplying two 10-bit signals produces a 20-bit result. But what if your registers are only 10 bits wide? Typically, the 10 least significant bits are discarded and the 10 most significant bits are kept. This approach does not preserve the full precision of the multiplication, but it is usually acceptable in practice. Another issue you might encounter is manually verifying the binary result of the mixer. Binary multiplication can seem tricky if you're not familiar with it, but it's actually straightforward once you know the steps. In the slide, we want to multiply -3 times -3 to get 9. First, we represent the -3 in 2's complement form, invert the binary representation of 3 and then add 1, which gives 101 for minus 3. Next, the slide shows the operation minus 3 times minus 3. To get the correct result, one method is to assign extend the minus 3 values. Remember that the most significant bit in 101 is the sign bit. By sign extending, we increase the number to 6 bits, 111101. This matches the expected length of the multiplication result, since multiplying two 3-bit numbers produces a 6-bit result. Next, we perform the binary multiplication and add the partial products to obtain the first result. The final step is to discard the two most significant bits, and as you can see, we are left with the desired result, 9 in binary. That concludes the slideshow presentation. Next, we will move to the Vivado demonstration, where I will go through the VHDL code for the example shown in the slide. The VHDL code, by the way, is in GitHub in a link in the description below. In the slide, a 90 MHz signal and a 100 MHz local oscillator are input into a mixer, producing output components at 10 MHz and 190 MHz, which we will observe in Vivado. Finally, I will walk through the steps of setting up the FIR Compiler component to achieve this. I will implement a low-pass filter with a 120 MHz cutoff, resulting in a 10 MHz output. Okay, this is the Vivado demonstration. As I said before, the code for this is in GitHub, and that's in a link in the description below. Let's first look at the source code for the mixer. I have the source code here in the sources window. Let's open that. Let's expand the window. At the very top, we have our libraries. Then we have our entity. We have our ports. Here we have a clock, and the test bench sets that at 900 megahertz. That's our sample clock coming in. Then we have two input vectors, A and B. Those are the two inputs to the mixer, which is a multiplier. They are 10 bits each. And then we have the mix out, which is 20 bits. So, okay, let's move on here. And this process right here is the mixer. It's fairly simple. It's clocked by the 900 megahertz clock. It says A times B is assigned to mix out signal. All these are standard. They're signed vectors. Each one is a signed vector type. And this is 10 bits, this is 10 bits, and this is 20 bits. So that's our mixer. Here I have the FIR Compiler component, and I'll show you how to set that up in the FIR Compiler GUI later. Here we have our signals. One thing to note is A and B coming in are signed signals, and mix out are signed. And a lot of the signals in the FIR Compiler are standard logic vectors, so we have to make that conversion in the code when we use the low-pass filter. This is the port map, the instantiation of the FIR Compiler. As you'll notice, it has a clock. That clock is the sample clock, and then it has a valid signal. These are AXI-bus signals, and they're not too hard once you get a little bit of experience with them. What I do with SAXI data T valid, S stands for slave, and so I set that to 1, meaning that the data that's coming into it is valid. The T ready signal signifies that the AXI-bus component is ready to accept data. And that is right there. It's an out. The next one is the data going in. And so T data is the data going in. And then T valid is coming out of the low pass filter component. I believe that's coming out. That's coming out. And that's saying the valid that's coming out of the low-pass filter component is valid. Now, interestingly enough, I send that into the filter. I know I said that our registers were only wanting 10 bits, but it turns out that the low-pass filter component actually wants 16 bits. I tried to put 10 bits in it, but it wants to extend it to a nice 8-bit boundary or 4-bit boundary logic vector. And so it made it 16 bits. So that means I had to take my 10-bit signal and sign extend it through the standard logic conversion, resize, and that made it 16 bits here. This sign extended mix out, which is the mixer output, except it's sign extended to 16 bits. That is actually put in on the input. T data is the input of the low-pass filter, and the output of the low-pass filter is MAXI data, T data. So now let's take a look at our FIR compiler here. So this is the FIR compiler GUI, and I will show you how exactly I set that up. Double click on that. Okay, the first thing you need to do is put your coefficients in there, and so that means you need to design your filter. In this case, we have 63 coefficients. That number there tells you how many coefficients are in there. The coefficients are separated by commas, and make sure at the very last coefficient it doesn't have a comma after it. And then so how did I get these coefficients? Well, I just asked ChatGPT to design me a low pass filter with a cutoff of 120 megahertz. I don't recommend doing that. I recommend using a tool. There's a lot of free available tools that will allow you to design your FIR filter coefficients. ChatGPT is hit or miss. In any case, you put your coefficients in there. Here you have a filter type. You have single rate, interpolation, decimation, Hilbert interpolate. I use single rate. And none of this changes. Then you go to the channel specification tab. And I left this all the same, but here I changed my input sampling frequency to 900 megahertz and my clock frequency to 900 megahertz. And then in implementation, it's important to put your data width. Now here's where I put 10 as my data width, but as you saw in the component, it automatically made it 16. It likes 8-bit boundaries, maybe it likes 4-bit boundaries, I'm not sure, but it wants to make this a 16-bit input, which means that the sign is extended into the 11th through 16th bit. And what else? Full precision. That gives you a number of options, including truncate LSBs, but I kept it at full precision, and that means that our output is now 29. We started out with an input of 10 bits going into our mixer. We came out with 20 bits. We tried to make it go back down to 10 bits by truncating it, but then this filter wanted 16 bits, so we signed it extended to 16 bits, and now we have a 29-bit output. And once again, you can throw away your least significant bits, and if your registers can't work with 29 bits of output. So I didn't change anything on detailed information implementation, and I didn't change anything there. You can add a reset to your filter here. Didn't do that. And the summary, I found the summary useful. In some cases, I find it for example, like you can see our coefficient structure is non-symmetric. What happens if your coefficients are symmetric? If your coefficients are symmetric, it would say here, but the thing it would do is it might change your cycle latency. So if you have 4 filters in parallel and you have some non-symmetric and some symmetric coefficient structures, well, it might change your cycle latency, and so that one might mess up your design. Some of the signals going through the filters will come out ahead of the other signals because of the cycle latency has been adjusted, because it can take this GUI is trying to be smart and take advantage of symmetric coefficient structures to make the implementation take up less resources. So, but that could cause different latencies in your signals if you have parallel filter structures. So there is a way to take care of that. So there is a way to take care of that, and it's in the implementation tab, and you can click non-symmetric. And for your symmetric coefficient structures, if you click non-symmetric, then all your filters will have the same latency, which in this case is 69 clock cycles. So that's all I want to say about that. So anyway, you can click OK. And since it's already implemented, let's take a look at the test bench. Here's the test bench, expand the window. And here we have our clock period of 1.111 nanoseconds. That's about 900 megahertz. We have our signals A, B. Those are the inputs to the mixer. The mix out is the output. Our frequency is 900 megahertz. Our frequency A is 100 megahertz. Our frequency B is 90 megahertz. And the maximum sine 10-bit output is 511. Here's our entity of our mixer. We have the clock, the A, the B, the mix out. This is our process. This is our sine wave generator process. And here is actually the sine of phase A and the sine of phase B. And phase A is calculated here. So phase A and phase B. So this generates the sine wave of the two inputs to the mixer. And so that's it for the test bench. And now let's run the simulation. Okay, let's expand the simulation here. So I don't know if you know this, but this is the ape input that the test bench is generating, and it's a nice cosine wave or sine wave. But I don't know if you know this. When initially you run the simulation for the first time, the waveform is going to look like this. It's going to look digital. And what's really nice about the Vivado simulator is you can make it an analog waveform. Now, if you notice in this case, I made it analog, but it doesn't look like a sine wave. That's because I have assigned digital waveform. So that means I have to go to radix and check sine decimal, and then it turns into sine wave. So that's a really neat feature of Vivado that you can do that. And there's one more tip I have here. If you go to waveform style and analog settings, it's set to the Y ranges to auto. Sometimes the tool has an issue and you will see nothing but a flat line there, even though there's something there. And the way you get around that is you click the fixed radio button and you put in values for min and max like that. And that enables you to see the waveform that may be there but isn't being shown automatically. The right value should be around 1,000, so let's put in the right values so you can see the whole waveform. There you go, there's a whole waveform. So that is very helpful. In case you lost your data, go to waveform style analog settings and you might be able to find it again by using the fixed radio button. So anyway, here's the analog in, the A input, and I believe that's supposed to be 90 megahertz, and the B input is supposed to be 100 megahertz. And then we want to look at what the mux out is. And mux out, let's expand this a little bit so you can see it better. Mix out trunk should be fine to look at. Okay, let's fill the whole window. Zoom in a little bit. So this is the mux out. As you can see, it's got this slower speed sinusoidal signal, and that's running at about 10 megahertz. And then it's got this really fast sinusoidal signal, and that's 190 megahertz. So that shows you that our waveform, our mixer is working as expected. And then the next thing we want to look at is what happens when we low pass filter this. And here's the result here when you low pass filter. You get your 10 megahertz signal out. So there you go. That's the end result. We basically, what we did there is we took 90 megahertz in, we mixed it with 100 megahertz, and then we used a low pass filter to downsample or downconvert it. And so now we have our 10 megahertz signal. Well, that's all for now. I hope you enjoyed this video. If you liked it, please like it and subscribe to the channel. Stay safe, and I'll see you in the next video.